Alrighty, so this time what I'd like to do is talk a little bit about what's called the Mandlebrot set. It's very interesting bit of math, kind of theoretical math. I don't know if it has any real application. However, there's something really interesting to watch or to see once you understand how the Mandlebrot set works. So, what is the Mandlebrot set? Well, it's basically that set of numbers which matches a certain criterion. And the criterion is this. If we take a function, so let's say we have some function f sub c of z, and we'll see what these indices mean in a little bit. The function is z squared plus c. And a Mandlebrot set is that set of numbers c, which when you iterate 0 into this function, the answer you get out, the output of iteration, does not blow up to infinity. Okay, so the Mandlebrot set, it's composed of its elements. So M has elements. The elements are that set of numbers. Now, this is definitely not formal mathematical symbology I'm doing here, but M is the Mandlebrot set. This epsilon symbol basically means elements of, so for instance, what composes the set? Well, it's these pieces, these elements, are the numbers which, when iterated, under 0, stay less than 2. Okay? Because it turns out that if at any point, and we'll see what this kind of means in a little bit more specifically, if we plug a number in and we iterate and we get numbers out, if the number at any point that you get out is bigger than 2, it inevitably will blow up to infinity and thus is not part of the set. So the set are the numbers which, when you plug it into this function, you get a number which is always staying somewhere between -2 and 2. Alright, so how does it work? Well, first of all, we say, okay, let's try f of 1, 0. So again, this is the function, z squared plus c. Z is any number. We just plug a number in for z. C is set. That constant is set. And that's the number that we're going to see. We're testing. Does it belong in our Mandlebrot set or does it not belong in the set? So C is the number we're going to test. Z is like a starting seed. It's, what number are we going to start off with and then see what happens later. And for the Mandlebrot set, you always start it as 0. So Z starts as 0. The C we're testing for this particular example is 1. So the first one, not the first element, but the first iteration goes 0 squared plus 1. And of course, when we do that, 0 squared is 0, plus 1 is 1. So we get the answer out, we get 1. Then we iterate, we keep iterating. We take this answer from one output and plug it back into the function and just keep going over and over, cycling, until we see either that the output we get stays within -2 and 2 forever, or it tends to infinity. It gets above 2. So let's try another step. We now take this 1 here, and now we're going to go, okay, f1 of the new element, which is 1, equals, okay, and now we have 1 squared, because z is now the answer from our previous attempt. So 1 squared plus, c is still 1. We're still testing the number 1 for c. So plugging these numbers in, 1 squared is 1, plus 1 is 2. Uh-oh, we already see we're already at 2, so we're not staying less than 2, but let's keep going. Now we have 2 as our number. So f1 of our new element is 2. Okay, well, it's 2 squared plus c is still 1. So 2 squared is 4 plus 1 is 5. And now we see, obviously, every time we iterate, every time we take the current answer and plug it back in as the input for the next step, our answers are always getting bigger and bigger and bigger. And they will always get bigger because you're squaring the number and then adding 1. Obviously, that's never going to be reduced. It's just going to continue to blow up to infinity. So, we already see that the number c equals 1 is not part of the set. Because when we iterate 0 under this function with c equal to 1, the numbers blow up to infinity. So 1 is not part of the set. All right, well, let's try another example. Let's try f of 0. So now c is equal to 0 here. Excuse me. So we have z squared plus 1, which is, not plus 1, I'm sorry, plus 0 this time. And so the z, we are, our starting seed, z, is 0, so 0 squared plus c, which is our little subscript index, 0, and so we get 0. Okay, now we iterate f0 of our new element, this guy, which of course is also 0, so 0 squared plus 0 is 0, and you can see no matter how many times we do this, we're always going to get 0. So, c equals 0 is part of the set. Because when we choose c equal to 0, that's the second number. When we iterate 0 under the function, that is, the first number is z, our starting number is 0. We always start with 0. Then our answers never blow up to infinity. They always stay at below 2. And in fact, they stay at 0 specifically. Okay, perfect. Let's try one more example. This time, let's try, we could choose negative numbers for c. So let's try c is equal to -1. So of course, the first element, we always start, our starting seed is z equals to 0. So z squared plus c is 0 squared plus -1. Which is -1. Okay, so now we iterate from -1 of our new answer, which is -1. So now we have -1 squared plus -1. -1 squared is -1 plus -1 is 1. 1 plus -1 is 0. Okay, now we iterate again, f of -1 of our new answer, which is 0. And uh-oh, we got back to where we started, 0 squared plus -1, which is -1. And we can see we're just going to cycle from -1 to 0 to -1 to 0 to -1, and forever and ever and ever. It's never going to be anything other than that. So, no matter how far we iterate, we're always staying less than 2. We're staying bounded. C equals -1 is part of the set. And now you can see this is how the Mandlebrot set is built up. We have a function, z squared plus c. We're going to set our first z equal to 0. And now we choose numbers c and test by iterating over and over and over and over, and seeing, does the output ever reach 2 or bigger, or of course -2 or smaller. Because if so, then eventually, even if it takes a really long time, the function is going to blow up to infinity. Or it'll eventually not blow up. That is, it'll stay within -2 to 2. It'll either kind of go to a fixed point, or it'll bounce back and forth between 2 values, or 3 values, or 100 values, whatever, but never ever getting outside of the 2 range. That's the other option. So if the C that you chose stays within the range of 2, he's part of the set. If the C that you choose eventually, and it may take lots and lots of steps of iteration to finally see it happen, but if you choose a C where at some point the output is 2 or bigger, then you know, it's fated to eventually blow up to infinity, and so that C is not part of the set. All right, now, what's interesting is we can, of course, draw the number line. Well, let me do it in black here. We draw the number line and say, okay, here's 0. Maybe 1's over here to -1, -2, so on. And we can mark off points on the number line where they are part of the set and points which are not part of the set. So we saw, of course, we know 0 is part of the set. We know -1 is part of the set because we tested it. We know 1 is definitely not part of the set. And it turns out it's going to look something like this range of numbers here. I think even past going negative, all of that is part of the set. Okay. So anything bigger than some number here, and you could actually try to figure it out. It's not that hard to see. It's a normal number. It's a rational number. But any number that's marked off on this number line, those are numbers that are part of the set, and then any number that's bigger than that particular number is not part of the set. All right. Well, that's not all that interesting. It's a fun little exercise. You can test your programming skills to see, have the computer come up with what numbers are in the set and not, and so forth. But what gets more interesting is we don't just have to let C be a real number. We can let C be complex. So, for instance, you could have C equals 2 plus 3i, and then do your F equals 0 squared plus 2 plus 3i, and then iterate over and over and over and see the exact same thing. Do you stay within this range of 2? And now when we say range of 2, we have to be careful because a complex number has 2 components, a real and an imaginary, kind of like a vector has x and y components. And so when we say, does it blow up past 2, what we mean is, does the magnitude of the answer ever get above 2? So, of course, for magnitude of a number, let's say magnitude of A, that's the square root of the real part squared plus the imaginary part squared. And of course, I'm not using good mathematical notation. There's actual symbology for that, but just so we can see it as we're comfortable with the kind of physicsy notation. So we could choose complex numbers for our C. It doesn't have to be real numbers. I chose real numbers at first because it's easier to do the arithmetic for it. Once we start having complex C's, then of course figuring out if it's within, we have to do this kind of magnitude and direction type stuff like vectors, and it's just a little bit harder to work with the numbers that way, just off the top of your head. But if we do it, then when we mark off what numbers are in the set, the Mandlebrot set, and what numbers are not in the set, of course we would do it now on the complex plane, where these are the imaginary numbers and these are the real numbers, axes. And so, for instance, the number up here could be I, up on the y-axis, and of course over here is 1, things like this. Well, if we were to draw or fill in what the Mandlebrot set, what numbers are in the set on this complex plane, it would look something like this. And of course this is just kind of a bad drawing representation because I'm horrible with this kind of stuff, but it looks something like this. And of course it's symmetric about the horizontal axis, not the vertical. As you can see, we've got this cardioid shape on the x-axis there, so it's definitely not nice and perfectly symmetric. All of this stuff here, these shapes filled in, these are all numbers that are part of the set, part inside the Mandlebrot set, and all the white space is where there's no. Those are not in the Mandlebrot set. So the vast majority of numbers are not in the set, because if you start with a number bigger than 2, for instance, or whose magnitude is bigger than 2, then immediately you're going to be outside of the set. It's the ones that are closer in less than 2 that are a little bit more interesting. But that's kind of what this set looks like. So it's an interesting picture. It's got some interesting properties. When you start looking at it, there's things that pop up that you maybe would not necessarily expect. But it's really cool. However, the really, really cool part, the interesting part, which is kind of the reason I wanted to make this video, comes from what people do kind of beyond just knowing whether a number is in the set or not. Because if you choose some number C and it eventually blows up, let's say, so it's not going to be part of the set, well, some numbers blow up immediately. They're already, once you, the very first iteration, the answer you get is already bigger than 2. Whereas other numbers, maybe it takes 1,000 iterations before it eventually gets beyond 2. So you have this concept of almost like this number C that I chose is definitely not part of the set. It's like really, really opposite to being part of the set. That is, it blows up really quickly. Or you have numbers that are kind of close. They're almost part of the set. It takes so long before they finally blow up. But they do blow up, so they're not actually part of the set. But you know, if you only stopped after trying 10 steps, you would have thought it's part of the set because it's not blowing up yet. But it's tricky, it's really on the edge. So you have this kind of concept of how fast does it blow up? How far away from being in the set is it? And this is where it gets really interesting. What you'll find when you search on YouTube or other places are visualizations of the Mandlebrot set. And so what people have done is they'll draw this set up on a two-dimensional plane, and the set itself, those numbers that are in the set are in black. So these shapes I've drawn here, that's all filled in black. But then the rest of the picture is not bare white, but colored in different colors. And the colors that they choose to fill in are based on how quickly that number, because remember, each one of these pixels out here, these are all numbers. So this might be the number 3 plus 4i, for instance. So for each pixel, they assign a complex number, whatever number C is for that pixel. And then they say, okay, they test, is this number in the set? If it is, it gets a black pixel. If it's not in the set, then it says, okay, well, how many steps did I have to iterate before it finally reached 2? Or blew up to infinity, whatever they want to set their little parameters to be. And depending on what, how many steps it took, they assign a color to that. And so maybe if it took a very, very long time, maybe that would be in blue, whereas if it took a very short time, it would be in red. And then medium is somewhere yellow, green colors and things like this. And so they'll color all the pixels, all the complex numbers, in other words, based on that parameter. If it's in the set, it's black immediately. If it's not in the set, then depending on how long it took to blow up out of the set, that gets a particular color. And so it's a nice, pretty color, kind of looks psychedelic. Looks like you'd have to be on drugs to really understand what the picture's showing. But what's really even better than just this pretty picture you get when you do this is the programmers who are doing these visualizations, they will choose a spot. So maybe they'll say, let's look right at the edge, kind of right here. I'm going to look at this spot, and I'm going to start zooming into the picture right there. And so you start to zoom in, and this is all kind of, animated very well. And as you zoom in, you see all these structures within this picture develop. And it's all because of the colors. Of course, if you didn't have the colors, if it was all white, it'd just be boring. It's either black or white. There's nothing there. However, just by changing what color each number gets based on how quickly or slowly they blow up, you get these really interesting fractal patterns, and things repeat over and over and over. And these programs, it'll be a 4, 5, 10-hour video zooming in on the picture, getting more and more and more precise to a particular number. And you'll start to see things start to repeat over, like you'll get the whole Mandlebrot set, this picture that looks like this. As you zoom into this red point, all of a sudden you'll see that whole picture develop all over again within itself. That's this fractal nature happening. So if you've never known what the Mandlebrot set is, but you watch one of these videos, it's really interesting. It's a pretty cool video to watch this kind of fractal thing happen. You're zooming in, and it's got music and all of that stuff, pretty colors. Really, really neat looking video. However, to me at least, when you understand that behind all of that is pure mathematics, purely assigning these colors based on a particular mathematical thing, which is, how quickly, what was the rate of this particular iteration blowing up. So it has nothing to do with how we as humans would visually like to see the picture develop. It's purely coming from the math itself. And yet it's got these neat symbols and repetitions and everything that's quite amazing. So I wanted to explain what the Mandlebrot set is. That way, when you do see these videos on YouTube and things, you'll kind of have a better idea of what's really lying underneath the surface, which, like I said, to me is what makes it even more beautiful than just the video itself. So anyway, hope you enjoyed, and I'll see you later.